All right, so if there are no specifics, then we'll get into chapter 2, which is measurements. Measurements are not peculiar to chemistry. I mean, any of the sciences, you're going to do measurements. So, as always, we need to define what our terms are. Anytime you make a measurement, you're determining either a physical or a chemical property in quantitative terms. In other words, you can put a number to it. Now, you can make observations like the solution turned blue and that type of thing, but that has very limited application. It's sort of an indicator of something happening, which is valid. But eventually you've got to put a number and a unit of measure to it. A number without a unit of measure is meaningless unless you know where the number came from. And most numbers that don't have units are the result of some calculation where the units were canceled in the process. But if you're going to make a measurement, you will nearly always have a unit of measure attached to it. So what types of measurements can we make? The sky's the limit, right? Anything that you can observe in the physical universe, you can measure. Mass, of course, is an obvious one. Now, we normally think of mass in terms of weight, but they're different concepts. Mass is a measure of how much there is. And that doesn't change no matter where you're at in the universe. But these are some other things that we're going to look at. Volume, anything that occupies space and has mass is matter. Everything else is energy or empty space. So these are some of the things that you can measure. So we need to standardize our measurements so that when we're discussing a law or a theory or any type of concept in the sciences, we need a common frame of reference. So we need to standardize what the measurements mean. We sort of grow up intuitively understanding what a foot is. You know, it's about like that. Or an inch is about like that. But for scientists, that's not good enough. We need an exact, as accurate as possible, standard of measurement to go by for each of those various commodities. English system is what we're used to in this country, if you're not in the sciences. And we're talking about pounds and miles. But if you're in the sciences, you sort of have to live in two different worlds because the sciences demand that you use the metric system simply because everybody else in the world uses it. So the metric system is governed by a body that goes by the French acronym, the System International. I won't bother you with the French pronunciation, but it's called SI. And all the sciences are governed by that measurement system. And it's more convenient to use, actually, once you get used to it, because it's based on the decimal system. So if you write something like, I don't know, that, and you want to compare that to it, you know that this one is about 1/10 the size of that one, simply because our numbering system is based on the decimals. It hadn't always been that way. In ancient times, well, you don't want to know. It splits your head open if you don't grow up with it. So the decimal system is valuable because all you have to do is just move that point, and you've got a different unit, different size. Okay, so science uses the metric system, and we have the authors of your book settle on base units. But actually, the SI system starts with fundamental units. The base unit isn't always the fundamental unit. The fundamental unit is the one that is accurately defined by the SI Commission. They say this is how much it is. So the kilogram is based upon a platinum iridium alloy cylinder of about that size. And that's your standard. And everything else in the world is compared to that standard for mass. And they keep it under lock and key and heavy guard and in a double bell jar with an inert atmosphere to try to keep it from changing over time. You don't want your standards to change. And if you have what you think is a kilogram in your lab, but you need to know accurately to several decimal places what it actually is, then you send it to these people and they compare it to the standard. And then they send you a report that says, okay, your kilogram actually has a mass of 0.999835. So then from then on, you can, when you standardize your equipment based upon that kilogram, you can set it to that value rather than what you think is a kilogram. Okay, so fundamental units are one thing. Base units, sometimes the base unit and the fundamental unit are the same. Come in. Be sure and sign in when you get a chance. And grab one of the PowerPoints. Sometimes, like I said, the base unit and the fundamental unit are the same, but not necessarily, not always. And I'll try to make note of that as we proceed. So in this case, the base unit is not the kilogram for mass. The base unit is the gram. Right? And the gram was inherited from way back. But the gram is in the neighborhood of that size of material. So if you use that for your standard, for your fundamental unit, think what would happen if you got a scratch on it or a fingerprint. For something that size, the percent error there would be huge. So they had to go to something larger, and they were stuck with a gram. So they said, okay, we're going to make our fundamental unit the kilogram, 1,000 times that. That's big enough to where you're not too concerned about corrosion or fingerprints, even though they do take precautions. They only handle this thing with special gloves. And they keep it in a temperature stable environment. It used to be in a cave because they're always stable. But they might, now that we have temperature control that's fairly reliable, they might have brought it up to the surface. Okay, so sometimes the unit that you want to work with when you're measuring something is not the right size. In other words, if we're measuring something that's the size of a viral particle, if you want its mass, it's going to be pretty small. And you're going to have to use lots of zeros in your decimal before you get to a non-zero number to measure the mass of a cell. So you want to change the unit of measure, and you need prefixes to do that. Let's see. I need to keep watching my hard copy so I know what's coming. Yeah, it is the next slide. Okay, so these prefixes are based upon the Greek. And they have specific meaning. So if you have your base unit, even though that's the fundamental unit, the base unit, in fact, the fundamental unit uses a prefix on the base unit, the K, which means 1,000 times. So 1,000 grams is equal to a kilogram. Okay, because this information here is stored in that prefix. Think of it that way, and I think it's easier to understand. So if you have something that's 23 kilograms, you want to know grams, you just take that K. What does it mean? It means 1,000. Right? Put 1,000 out here in the grams. See, that's from here, and then 23 times that. So it's 23,000 grams. That's what the kilo means, 1,000 times. Mega means 1,000,000 times. And giga means 1,000,000,000 times. Everybody knows gigabytes, right? Storage for your computers. That's what it means, giga. 1,000,000,000 bytes of information. And then you can go fractional. These are multiples. You can go fractional, right? You can say a tenth or a deci, whatever. Or a centi, which is 100th. A centimeter is 100th of a meter. So how many centimeters would they be in a meter? Well, if each one is 100th of a meter, it should take 100 of them, right, to make a meter. Milli, we know millimeters, we know milliliters. If you work in a lab or you work in the medical area, you know what a milliliter is. It used to be called a cubic centimeter, but they're exactly the same. Same size, milliliter, cubic centimeter. Micro, a millionth of something, or nano, a billionth of something. So nanotechnology is on the size scale of a nanometer. Very, 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 very small. And then when you get down to the size of an atom, you're talking about pico, which is 10 to the minus 12. Okay. So all those prefixes are useful if you don't want to have a number with a bunch of zeros before you get to the value that you're looking for, the non-zero part. That's what the prefixes are good for. If you have something bigger than that, like distance from the Earth to the sun, average distance is 150 million kilometers. And astronomical units, actually, I'm getting off topic now, but in astronomy, you use even different units than that. Like astronomical unit is the Earth's average distance is 1 unit. Or if you go outside the solar system, you may discuss distance in terms of parsec. It has its own definition. Or if you really go far out, you're talking about light years. So we're not going to delve into that. Chemistry doesn't deal in those size values. Okay. So you got these prefixes that allow you to change the size of your measurement. And because we know the relationship of each one to another, you can convert them from one to another. Right? If you have, let's say, example, let's say we have, let's see, how far is it from, I don't know, from here to Charleston? About an hour, about 60 miles. Okay. 60 miles, let's see, that would be about, well, let's just make it easy on ourselves. Let's say 100 kilometers. Probably a little less than that. But we know that this is our unit of measure. Let's say we want to know what it is in meters. Right. Say we have a formula that requires the input of information into variables, and it's strictly limited to a certain measurement. So we have to convert this to meters in order to use that formula. Okay, that happens a lot in chemistry and physics. So if we want to convert that to meters, we need the relationship between meters and kilometers. Now, why did I put them one on top, one on the bottom, because this is the one you want to keep. And right, that's always in the numerator. So this is in the denominator, and they cancel and leave you with the unit you want. So you just need to know the relationship between the two. Well, one of these is worth 1,000 of those, right, because of the kilo. So then 100,000 meters from here to Charleston. Okay, we'll talk a little bit more about unit conversions later, but I just wanted to make the point that these things are interchangeable. See, nature just does what it does. And it has various distances, sizes, whatever the case may be. And we invent these ways of describing them. But if you look at it from nature's point of view, nature could care less. It just does what it does. Okay, so the fundamental unit of length is the meter. And the meter originally was defined as a fraction of the distance from the equator to the North Pole. But it wasn't just anywhere on the Earth that you could do that, because we know that the Earth is not a uniform sphere. It's pretty close, but it's not exact. So they had to define, well, where are we going to measure it? Right? You know about longitude and latitude. Latitude is north or south of the equator. Longitude is east or west of a defined 0 point. Well, that defined 0 point goes through an astronomical observatory in Greenwich, England. That's longitude 0. So anything east of that or west of that is defined in terms of degrees, angle degrees. So we said, okay, well, we're going to go through Greenwich then, from the equator to the North Pole through Greenwich. That distance is our starting point, and then we take a fraction of it so we can get something manageable in size. So that was the original standardized meter. And once they agreed upon it as an international scientific community, they said, okay, now we need some fixed object that we can use to compare all other meters to that. So they took that same alloy, platinum iridium, because it doesn't corrode, and they made a bar that's a meter long. That would be about a yard, so a meter's a little bit bigger. And it has a funny shape to it. It's like something like that. The same thing on top. That's a cross section, and then it's like that long. Now, I think they chose that shape because of that shape stabilizes its length better than just a simple bar, because a simple bar might warp like this, but that one won't. And then you do the same thing. You just take your meter and you package it nicely, or you carry it there yourself and say, how close is mine to yours? And they tell you. Well, that's the way they used to do it. Now, if your laboratory has the money and the will, you can buy an instrument that will tell you the meter exactly, because now it's based upon a certain laser formed from a certain element, and then you count the wavelengths. So you count so many wavelengths, there's your meter. And it's actually more exact than the bar. But they haven't been able to do that for the mass yet. So we're still stuck with that cylinder. Okay, so let's see, I must have accidentally punched the button again. Okay, we're done with that one. So like I said before, the gram is the base unit, but the fundamental unit is the kilogram. So what is the difference between mass and weight? Well, like I said, mass is a measure of the amount of something. Doesn't matter where it is in the universe, that same amount is the amount you started with. Weight is a measure of force. So when I say I'm 200 pounds, well, I'm 200 pounds on the surface of the earth. But if I come close to a different size heavenly body, then it's going to draw me, gravitationally pull me with a different force based upon my mass. My mass hadn't changed, but the attraction between the two has changed. And that's based on Newton's law of universal gravitation. It just says that the force between two objects that's a proportionality constant, is size of the big mass and the size of the little mass divided by the square of the distance between them. So if you get closer, then the force is going to be greater. Or if you have bigger masses, like my mass didn't change, but the mass of the body I'm standing on, like the Earth or the Moon, will change. So if that changes, then the force or my weight will change. But the mass is constant for that object. So on the surface of the Earth, I might weigh 200 pounds, but on the surface of the Moon, I might weigh 6 of that, 35 pounds. But I still have got the same mass. Okay, let's see. You know, your weight even varies on the surface of the Earth, depending on where you are, because the Earth is not uniform in distribution of its mass. They noticed that with the Moon. When we started orbiting the Moon with satellites, based upon a uniform mass of the Moon, we know the satellite should be here. But it wasn't. It was over here. And they finally figured that out. It's not uniform mass throughout. In fact, it's heavier on the backside than it is on the front. It's got a thinner crust on the front than it does on the back. But then I digress again. So volumes. What's our standard for volume? Well, the fundamental unit for volume is the liter. Well, actually, it's a base unit. Actually, that's not right. The liter is not a fundamental unit. I need to correct that slide. The liter is a base unit. The fundamental unit is the meter. And you derive volume from length. We only have to define the length, and then you derive volume from that. So what would be a volume for a meter? A cubic meter, correct? Cubic meter would be a derived value for volume. But nobody works in cubic meters. At least not in the chemistry lab. So we need a relationship. How do we relate this fundamental unit to liters? Well, you have to shrink this down some more. So if you have a cube like this, right, with a meter on each side, then you take a tenth of that meter down here. So what is that? That's a decimeter, right? This unit right here. It's a decimeter. It turns out that a cubic decimeter is a liter. Or we can convert using other units. And once we settle on what that is, then we can forget about this and standardize things based upon whatever base unit we decide to use. And the base unit for volume is the liter. Right? If you ever travel outside the US, you'll be buying gasoline in liters. Well, I guess that's okay, except that when you pay $4 a liter, how much is that a gallon? Well, it's almost 4 times that, like $16 a gallon. Makes it a little less because you ever look on a gallon jug of milk? They put liters on them now. So 1 gallon equals 3.8 liters. I always look at labels, read labels for whatever information is there. I don't know what that is. Maybe I'm quirky. Or no, I got a master's degree in food science, and we had to design labels for food products as one of our classes. So I know what's supposed to be there, or what was supposed to be there back in 1975. I don't know what it is now. Anyway, these are interconvertible, right? 1 gallon, this is the English system, and this is the metric system. So we can convert back and forth in volume between the two, because we know what the relationship is between the two. And if you're in the medical profession, you might see some old syringes maybe that are marked off in cc's. You know, they may still be in their packaging. You look at them, they say cc's on them. That means cubic centimeter, because printing in ancient times was difficult to do with superscripts. So they said, okay, instead of doing that, which would be the proper way, we'll just abbreviate it, cubic centimeter, cc. But eventually, we're sort of migrating toward the metric system. We needed to use something that's common to the rest of the world, and that's the milliliter. The milliliter, milli being 1,000th of, is 1,000th of a liter. So 1 milliliter is equal to 10 to the minus 3rd liters. Okay, or like I said before, if you have, say, 25 milliliters, you want to know how much that is in liters? Take this one. What does that equal to? That's 10 to the minus 3rd liters. So that part becomes 10 to the minus 3rd, and then you have 25 times it. And you can convert quickly that way. Or you can use the dimensional analysis that I was using earlier. Okay, so let's see. This relationship is important for you to remember, because sometimes your calculations come out in cubic centimeters, simply because of the way the units that go in will give you a certain value when they come out. And if they come out in cubic centimeters, but you need to use it further in terms of milliliters, just change the value. It's exactly the same size. Okay. Oh, I wasn't looking ahead. This I didn't have to draw that. It's already on a slide. So here you have a, let's see, what is this? Volume of a cube, 10 centimeters. Okay, so this is 10 centimeters. So what's a centimeter? 1 centimeter is a 1/10 of a meter, correct? No, 100. 100th of a meter. And a decimeter is a 1/10 of a meter. Right. So what's the relationship? Well, this one is 1/10 of that one. Or this one is 10 times the size of that one. I'm getting blank stares. Okay. So suffice it to say that once you get down to this level, that's a centimeter, cubic centimeter is 1 milliliter. And 1,000 cubic centimeters is 1 liter. So a liter is the base unit for volume. Even though it's not a fundamental unit, it is the base unit. Okay. Let's see. I don't know if we need to spend a lot of time on this one. These are base units for length. The meter is the base unit for length. It's also a fundamental unit. Mass, the fundamental unit is kilograms, but the base unit is grams. And volume, the base unit is liters. But the fundamental unit is still cubic meters. And the beauty actually of this international system is the interchangeability of units of measure. In other words, if you know one, very often you can convert to another one. For instance, I use this one because I know it. That's Newton's second law of motion. It just says that if you have a known mass and it accelerates at a certain speed, the required force to make that mass accelerate is this. So that's the relationship between force, mass, and acceleration. Well, let's look at it in terms of units of measure, right? What's acceleration? Well, acceleration is in meters per second squared. In other words, acceleration is a change in velocity. Velocity is meters per second. So if you change the velocity, you need another time unit in there. So it goes, you're changing meters per second. Okay, so that's the units measured for acceleration. This one's kilograms, the unit for mass. So the force would be in kilogram meters per second squared. But we have another unit for that. To honor Newton, we call that 1 Newton. So one of these is 1 Newton. But if you have a calculation that requires the use of a Newton as force, but you want to be able to, you're looking for an answer in your calculation that's either meters or kilograms or seconds, whatever the case may be. If you just use Newtons, then you're stuck because you can't cancel into the others and end up with the one you want. So knowing that this one is equal to that one is important when you do calculations. And I'll point those out as we go along, if that's the case. You know, I can't remember how far we're going to get in this class with that, but I know in the general chemistry class we'll dig a little deeper and do more math, but you might be safe in this class. Okay. So occasionally we have questions to see if we got the point. All right. So which is the largest of this group? Well, obviously the kilogram. If gram is the base unit, then this is smaller than a gram, and this is smaller than a gram, and that's bigger than a gram, simply because of the prefix. Okay. Now we're going to look at, let's see. I'm going to look ahead a little bit to try to organize this information so it'll make more sense. Okay. I probably ought to organize these slides a little better. Because I inherited them this way from the authors, and the authors, I think the authors are kind of harebrained the way they present stuff. I don't know if you read through your book and had that same feeling. No? Okay. Well, that's good. If it's getting through to you, then don't mind me. So let's take it in, I will take it in their order. But I will preface everything that's going to be said in the next few slides with the fact that every measurement that you make in any of the sciences has within it uncertainty. You can never be sure that the number you measure is exactly what nature believes. It's a certain length. This, whatever it is a certain length, but when we measure it, we're introducing uncertainty. For instance, if you want to measure something like that and you put your meter stick up to it, right? It's got markings on here. Well, if your eye is looking from this angle right over here, right, you're going to see it this way. Right? Or you look up, we're measuring this length right here. Measuring like this. So we're going to say, okay, it's that long. But what if you get your eye off to one other side over here? Well, now you're looking at it like that. Okay, now you think it's that long. That's known as parallax error. You're off to one side. That happens a lot in measuring volumes and temperatures with a thermometer. So I'll show you how that's how we try to minimize that error. Now that's just error due to the observer, but there can also be error that's introduced by the device itself. Now, if you never had this meter calibrated by comparing it to the original, then it could already be wrong. Okay, and that's probably the case in student labs because we're cheap. We buy cheap stuff. You just got the experience, right? You're not using really accurate, high-end metrics. Okay, now that I've said that, well, let me introduce one other concept. When we write a number, something like that, if we've got a number that's with a unit of measure, and some other scientist looks at that number, they instantly know that the numbers that you're claiming, the digits in that number that you're claiming are exact, are accurate, have no error in them whatsoever, are these. Those are called the certain digits. Okay. The last one is always assumed to be uncertain. Another word for that is it's a guess. Okay, so when you write your numbers, if you want somebody else to read them and not throw away information that you wanted them to understand, then you need to be sure that the last digit in your number is the guess. For instance, if you're reading the volume of something in a cylinder, and it's got markings on it, and it's got sub-markings, like that, and the volume is maybe right in here. Let's see, let me get a little closer there. Say the volume is like that, okay? So we filled it up with something, and it's got a concave meniscus on it. So that's where you always read at the bottom of the meniscus. So what's it going to be? Well, let's say this is 10, 20, 30, 40 milliliters on these main marks. And then in between, there's, let's see, we should have 2, 4, 6, 8. We should have 5 steps in here. So within those, you've got 2, 4, 6, 8 milliliters. Okay, so what are you going to write for this number? Well, let's see. We know it's between 30 and 40. You know, somewhere in there. Where's the next mark? Well, the next mark is 2, 4, is 4. So we know that 34 is accurate. It's certain digits. So what's in between? This is a bad example. I can already see the problem because we've got 2 milliliter jumps. So it looks like it's halfway in between 35. Well, let's say for argument's sake, we know that it's 34. And then in between 34 and 35, it's halfway in between. There's no marking for it. That's the point I'm trying to make. There's no mark on there. So the last number is the guess. What do you think it is between those two marks? The marks are the certain values. So let's say it's halfway between. So 34.5, we know that these are certain and that one's uncertain. Okay. Now that I've said that, we need to talk about how do scientists identify these digits. This is a general discussion of certain and uncertain, but there's a more accurate actually discussion that involves significant figures. And the reason we introduce the concept of significant figures is because when you start to do calculations, you need to have some method for knowing how many of these certain and uncertain, certain and then one uncertain digit can you have in your answer. And just because your calculator gives you 9 decimal points doesn't mean you can keep them, because a calculator doesn't think in those terms. You've got to decide how many you can keep. And that's what significant figures and calculation rules for significant figures addresses that problem. Okay, so we got types of numbers. The exact number has infinite significant figures. In other words, use this in a calculation, you don't have to even think about it after that. In other words, if you make a calculation with all exact numbers, then you can have as many decimal points as you want. And exact numbers are usually counting numbers like 12 objects or conversion factors. Anytime you have a conversion factor, you can treat it as an exact number. In other words, you don't have to consider it as a limitation on your answer. All right, we've discussed that already. Let's see. Actually, we've talked about this also. Certain digits versus uncertain digits. The last digit is uncertain. Oh, here's an example. This is a good one. So if we're measuring this thing right here, and it's the same object on both of them, but with this measurement, you've got a different scale than you do for this one. This is a finer scale than that. So the length here is somewhere between 3 and 4. That's all we're certain about. So 3 is certain. The last one is a guess. Between 3 and 4, it's a tenth of something. So we're going to say that's about 0.7. That's our guess. So 3 is certain, 0.7 is uncertain. Whereas if we use a ruler like this one that's marked off in millimeters, right? If these are centimeters, then a tenth of a centimeter is a millimeter, right? Because a centimeter is a tenth of a meter, and a millimeter is, hundredths of a meter is a thousandth of a meter. So the ratio of a millimeter to a centimeter is 10 to 1. 10 to 1. It's 10 times bigger. Well, this is 10 times smaller. So when you make 10 subdivisions of a centimeter, each one of these is worth a millimeter. Okay, so now we can say exactly our certain number is 3, and then this one is 7, and that one's 0.7 and 0.8. So it's between 0.7 and 0.8. Then you estimate the hundredth position. Right? You go into what's the distance between this mark and that mark. It's in the hundredths range. And this one is what we think to be that position. So that's our uncertain digit, that last guess. All right. Now, significant figures. I sort of introduced that topic already. We have to find which of the digits are the combination of certain and uncertain. How many of them are there? Okay. So here are the rules. Rule number one, all non-zero digits are significant. So in this case, you would have 3, 4, and 5 are certain and 6 is uncertain. All 4 of those are significant. That's the easy rule. If your number only has non-zero numbers, then you know that everything you see is significant. Then we have to deal with zeros. And there are 3 types of zeros. Okay. They're the leading zeros, that is, ones on the left. And the leading zeros are never significant. So you've got these 2 zeros out here, they're just placeholders. So these 2 non-zero numbers are significant. And notice how they write that number. They don't write it like that. That's what I call an orphan decimal. Decimals on the left have to be bracketed with another 0. And that's for practical purposes. Because when you put that number in a sentence, what's to say that's not the period at the end of a sentence? So it needs to be protected. So those zeros are not significant. Then you have captive zeros, those that are between 2 non-zero numbers. Now here we have 1 of them, but you can have more than 1. Those zeros are always significant. So this number has 4 significant figures. Non-zero, 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 and a captive. That's significant. Okay? And then you'll never guess what the third one is. One's on the right, right? So in this case, trailing zeros are conditional. The trailing zeros are significant only if there is an explicit decimal in the number. In this case, there is one right there. So these 2 zeros are significant. Suppose we wrote that number like this. Two significant figures. We know there's an implied decimal right here. That's the ones positions, the tens, the hundreds, the thousands position. But with significant figures, only explicit decimals will give you significant zeros. In this case, only the 9 and 3 are significant. So if we meant to make all of those significant, in other words, this is certain, that's uncertain, and those don't count. Oh, hold on a second. We have battery signal. I forgot to turn on the strip. Okay, we're good. So this is certain, that's uncertain, the way it's written. But if we really meant to say that this is certain, that's certain, that's certain, and this one is uncertain, then we better put a decimal. So in that case, we have 4 significant figures. Okay, now why are we going to all this trouble? Because we're going to use that information when we do calculations. Okay. Let's see. Well, first we need to also agree upon rounding, because if your calculator spits out 9 decimal points and you can only keep 2 of them, then you need to know how to round. And we're just going to keep it simple. Right? 5 or above, round up. Less than 5, round down. But it's important to know where is that 5 or above or below 5. If you need to round to this position right here, you only look to the right, one place. Ignore the rest of it. In other words, you don't round this one and then round that one and then round that one and then round that one. You're asking for trouble if you do that. So you only look to the right of the position you need to round and say, all right, that's less than 5. So we just truncate there and leave the 2. Or this one, the 6 is greater than 5. So we're going to round that one up to 1. So 5.01, there you go. And notice what it did. Well, actually, it didn't do much. These are captive zeros to begin with, and there's still a captive 0 in there. So. Okay, now that we know how to round, we can do calculations with our significant figures. And the operational rules come in 2 flavors. One is multiply, divide. That's the easy one. Or add, subtract. Multiply, divide simply says that when you have 2 or more numbers that are multiplied or divided or any combination, and that's all you're doing, multiply, divide, you look for the smallest number of significant figures in the calculation and apply that to your answer. So in this case, we have 4 significant figures and 3. So if our calculator says this, we have to round to 3 significant figures. 1, 2, 3. There. Since this is 1, we just truncate and keep the 5. Okay. So if you have a calculation that's got several steps in it, and they're all multiply, divide, in order to avoid rounding errors, if you round at each step, then what would happen? Well, potentially, if this one rounds up for that answer, and then this answer goes into another calculation, and that answer rounds up, you could round up 3 or 4 times and end up with the wrong answer. So what I like to do is, if they're only multiply, divide, then calculate keeping all the decimal points you can in each step. And then you go back to the beginning and say, all right, which one was, or intermediate steps, right? Because you may have numbers in there that are different significant figures. You look through all those calculations, and the ones that are actual measurements, but not the product of a calculation. Look for those significant figures and find the least one in that group. And then apply that to the end. And your rounding errors are significantly reduced. Then there's add, subtract. If you've got any add, subtract in there, then you have no choice. You've got to do the significant figures with each step. Okay, so what's the rule for add, subtract? We'll line up the decimals. You line up the decimals on your numbers and then add everything together. And then you say, which ones can I keep? Well, the one that has the fewest number of decimals, right? So you're limited right here. That means you have to round and keep that 7. So this one has 4 significant figures. This one has 2, and your answer has 3. Okay, based upon this rule. So you can't tell how many significant figures your answer is going to have in an add, subtract simply by looking at the numbers. You have to do the math. Now, the reason I pointed out here the uncertain digits is because suppose you don't have any explicit decimals in there. Right? Suppose you've got to add 2 numbers. And let's say this one is like that. Okay. You would line up the implied decimals and then add it together, right? Just like any math course. There you go. But how many of those can you keep? That's not significant. There's the uncertain digit. There's the uncertain digit, which is smaller unit than this one is. So you have to draw the line there. That means with this one, we would have 4, 7, and then a placeholder for where the 5 was. So this would be the answer for that. I haven't found any textbooks yet that take into account that possibility. So that's why I always bring this up in discussions, right? Line up the decimals, fine if you got decimals, yeah, no problem. But what if you don't have any decimals? Then you line up the implied decimals and then you look for which are significant, right? That's not significant, so you have to stop right here. Okay, so we got our rules now. Now, the problem is, let me see. Better check myself. Well, I'll paint myself into a corner. Oh, I do have an example for that. The problem now becomes, what do you do if you have a mixture of add, subtract, and multiply, divide? We need to know the order of operation, right? So we go back to math class. So what am I thinking of? Anybody remember that? Order of operation. If it's not explicitly, well, actually, this takes into account explicit definitions of orders because you do the parentheses first, right? If there are no parentheses, then you have to go to exponent, which is just multiply, divide. Well, not multiply, but you do the exponents first. Then you do multiply, divide, and then add, subtract. So parentheses are important if you want a certain calculation to go the way you intended. Otherwise, you could have something like times minus and then divide. Let's see. Well, let's do times again. Like that. Without any parentheses, you would do these two first, and these two, and then subtract. But what if we actually meant it to do this? Then you would do this first, and then multiply all the way through. So you get a completely different answer without that explicit. That's why I hate algebraic calculators. 1 + 1 = 2. Because you better put those parentheses in there or it's going to give you the wrong answer. But with my calculator, I don't need that. Reverse Polish notation. Once you understand how it works, it doesn't need parentheses. So I digress again. So we got multiply, divide, add, subtract, our rules. How about this one? Let's see. Add those two together. Right. We're going to have to be limited right here, correct? So there you go, and you're limited to this position right there, so you're going to have to round 10,700 once we round. Okay. Don't forget the 0 placeholders. They're not significant. So you're safe putting them in there. We're not saying they're significant. It's only if you make the mistake and put a decimal there, then you're claiming they're significant, and they're really not. And like I've said before, the only way to get comfortable with this stuff is just work a lot of problems. If I didn't say before, I'll say it again. Two best friends, you remember what you two, did I say that here? Your two best friends in chemistry?
Yeah.
Curiosity? What's the other one? Boredom. If you work enough problems that you're bored working that type of problem, then you're good to go. Okay, so let's say we're going to, this addresses the situation in a laboratory environment where you've got a series of measurements you're going to make, and you want to know, how reliable is my answer? Well, the reliability, the accuracy of your answer is based upon the least accurate instrument or measurement that you make in the sequence. So in this case, we've got two measurements of liquid, and we're going to combine them. So what can we claim for the answer? Well, we look at which one is the least accurate. This one right here. So it's going to limit. So we look at this one and say, we've got how much water in there? Right? 1, 2, not quite 3. So it'd be 2, 0.2, 0.4, 0.6, 0.8. It's sitting right on 0.8. So I would be tempted to say 2.80. Last one's a guess, because that one's right on the line. But I'm not sure if this slide is going to agree with me. Let's go ahead and see if it happens. How about the other one? Okay, this one is marked off in tenths and then fractions of hundreds, the hundredth position. So this is 0.2, between 0.2 and 0.3, but that's 0.02, 04, 06, 08. So that one's 0.280. So if we add those together, right, we can keep those 3.08. Okay, I did correct the slide. That's good. And what limits the precision of our answer? Actually, that's the wrong term. Right. Remember, we defined accuracy and precision, didn't we? Right. This is accuracy, not precision. We need multiple measurements to determine precision. So I mistakenly kept the wording from the authors, who obviously never read their own book. Right. The least accurate device in the sequence determines the accuracy of the outcome. Okay, and we go back to exact numbers. If you have a calculation that uses exact numbers, then you can ignore the significant figures in those numbers. For instance, 1 inch equals 2.54 centimeters. It may as well have infinite significant figures as far as your calculation goes. All right. So what are we going to do here? Calculator gives an answer of 8.8274 when you multiply 4.6 times 1.919. Which of the following answer rounded to the correct number of significant figures? Right. What rule is this? Multiply, divide. So we're going to multiply 3 significant figures. Right. That one's significant. Times 4. So our answer can only have 3. Correct? So if our calculator says this, we can go 1, 2, 3, round that up to 3 and throw the rest away. So it should be A. Okay. All right. Now we need another way to express very large numbers or very small numbers, because the unit of measure may not be convenient for what we're working with. So suppose we do have to keep a particular unit, but our number is huge or it's very small. Then we need a way to express the number that's a little more compact. And that's where exponential and scientific notation come in. They're not the same. Exponential notation, actually scientific notation is a subset of exponential. Exponential notation stores information from the standard number into the exponent of 10. So if we have something like let's just take Well, let's not do that. Actually, let's say that 150 million kilometers from the Earth, average distance from the Earth to the sun. Okay, so how many significance do we have? Only two, correct? All these zeros are not significant. So how would we express that in exponential notation? Well, exponential just says that you need a power of 10 times whatever's left over, which is called the coefficient. So we could move it over to here. Say we only want to store that much information. So the decimal went from here to here to here. And now we've got 1, 5, 0, 0, 0 times 10 to the third. And these still are not significant. Okay, that's exponential notation. Scientific notation is a special subset of exponential, in which the coefficient has to be between 1 and 10. So in order to make that scientific notation, we would move the decimal over to here. And we would say 1.5 times 10 to the what? 1, 2, 3, 4, 5, 6, 7, 8. 1.5 times 10 to the 8 kilometers is that number. So notice that when you move the decimal to the left, you're making the coefficient smaller. It's going from 150 million down to 1.5. So that means the power of 10 has to be positive and big. If we move the decimal to the right for some other number, then we'd be making the coefficient larger. And that means the number here would have to be smaller. They go opposite to each other. So let's say we have something else like something like that. We would express that in scientific notation. We would power of 10, we move our decimal place 1, 2, 3, 4. That would give our coefficient between 1 and 10. But it will be a -4. Because you're storing up a small number in that position. And then this would be 3.67. Notice also that your coefficient stores the significant figures, right? This one we know only has 2, right? Well, that one only has 2 also. And when you're looking at a scientific notation, a number in scientific notation, the significant figures are only based upon the coefficient. You don't have to look at the power. This one would have 3. That one only has 3 because all of these are not significant. And then when you go to do calculations with them, kind of hard to do add subtract with this type of arrangement. But if you do add subtract, you got to be sure that your numbers have the same power of 10. Right? Multiply, divide is no big deal. Right? You can do that with any combination of powers of 10. But if you're going to add subtract, and you do it by hand, then you got to match this value here. If we try to add these two together, it wouldn't work because they got different powers of 10. You'd have to make one of them the same as the other one, or you'd have to meet in the middle somewhere. So the power of 10 has to be the same if you're going to add subtract. Okay. Let's see here. What do you do if you got a calculation that gives you, let's say your calculation produces an answer that you know is that. What do you do with that? Well, you got to move the decimal one more this side, right? Because you can't have something bigger than 10. So you move it there, store that movement in your power of 10. All right. Let's see. What's wrong with this picture? Well, if we convert 300 to scientific notation, those two zeros are not significant, correct? So these two zeros can't be there, right? So this is what the authors produced. I didn't correct this. I'd rather make a point of this error that they made. 300 can't be 3.00. It would have to be just 3 times 10 to the second power. If we wanted it to be this, we'd have to put a decimal right there. This one's good. Oh, so if you've got, well, if you know how to put exponents, scientific notation into your calculator when you do a calculation, then you don't have to worry about it because it's going to spit the number back in scientific notation. But if you have to do it by hand, say you're in the middle of tests and your calculator goes on the fritz and I don't have an extra one, then what are you going to do? You got to do it by hand, right? So if you're going to multiply two scientific notation numbers, then you multiply, let's see, to multiply the exponents, you add them together, right? If you've got a number that's 10 to the 4th times 10 to the 3rd, then the answer is going to be 10 to the 7th. Say it's just 1 here. Let's keep it simple. 1 times 10 to the 7th. That's just the way exponents work. We could probably prove it if we wanted to take the time to do it, but I'd rather talk about chemistry. What if you divide exponents? Well, you subtract the denominator from the numerator, the exponent of 10. Okay, let's see. If we convert this one, all of those are significant, so we get to keep them all. But let's suppose that we're only allowed to keep 4 significant figures for some reason. The calculation says, your calculator says this, but you can only keep 4 of them. So you count from the left. 1, 2, 3, 4. That rounds this one up to 2, but these are placeholder zeros. Only until you write it in scientific notation. And when you do that, then you move it from, you go 1, 2, 3, no, 1, 2, right here, 2. So, oh, excuse me. I misspoke, of course. 1, 2, 3, 4, 5. So 10 to the 5th, but in the coefficient, we can only keep 4 positions. So this has to be rounded up to a 2, right? There it is right there. 6.302. Those look like the same numbers, don't they? Oh no, there's a decimal missing. Ah, attention to detail. So it is B. Okay, now conversion factors. We need to know how to use conversion factors because units of measures don't always jive with what we want. And the fancy word, the fancy description of conversion factors is called dimensional analysis, which just means keep track of your units. What are your units doing? When you multiply 2 numbers or you add and subtract 2 numbers, they've got units of measure with them. Then you got to do something with the units of measure too. You can't just throw them away. Right? The simplest version of that is a cube. That's a length the same length on all sides. When you multiply those lengths together to get the cube, the volume, then what do you do with the units of measure? You multiply them too. Also, same thing in converting from units, different units. So I'm going to explain to you why conversion factors work. Let's see. How much of this do I need to draw myself? Yeah, it needs some explanation. Okay, let's say you have I'm gonna try to keep it simple. Let's say you have something that's 254 centimeters long. And I want to convert that to inches. Well, what relationship do I know? Centimeters to inches. You need an equivalence to make a conversion factor. We have to know what's the relationship between the two measurements. If I want to convert that to inches, then I need to know that 2.54 centimeters equals 1 inch. Now, why didn't I put 1.00? Because I'm going to make a conversion factor out of it, and that means I don't care about significant figures. It doesn't matter. It could be 1.000000, just infinite. So this is the relationship. Okay. So what can I do with that equivalence? Mathematically speaking, I could, I don't know, divide both sides through by the same number. Let's divide both sides through by 2.54 centimeters. Can I do that? Mathematically speaking, yeah. If you do the same thing to both sides, then you haven't changed it. So I'm going to divide both sides through by the same number. Well, that cancels, and that cancels, giving you equal to 1, correct? So that means this fraction is equal to 1. Well, let's say if I multiply this by 1, I can do that. Mathematically speaking, I can multiply anything through by 1, and that's a valid operation. Problem is, it doesn't give me the answer I want. I want inches out of centimeters. Well, what's equal to 1? This right here. So instead of that, I put the equivalent to 1. 1 inch equals 2.54 centimeters. Now, is that going to get me what I want? Well, remember, whole numbers that are written just out free space, they're always in the numerator. So that means the units in the numerator too. And if I multiply two numbers, then the units, centimeters here in the numerator, centimeters here in the denominator, they cancel, just like they did over here. So centimeters are gone. And inches, I can't do anything with that because there's nothing to cancel inches. So I got to keep the inches. So I am going to have inches as my units of measure out here in the answer. Then I say 2.54 divided into 25.4 is what? 100. Right? 100 times this would be 254. Yep. So 100 inches is equal to 254 centimeters based upon this equivalence and the use of that equivalence to make a conversion factor. Now that I've explained it, that it's true, you don't have to go through this anymore. You just say, if you have an equivalence, you can write that in terms of a fraction. Either that way, or you can flip it. I can flip it, can I? If I need to, right? Because it's equal to 1. So if it's equal to 1 this way, it's got to be equal to 1 the other way. Okay, so that's why conversion factors work, because they're always equal to 1. Okay, sometimes one conversion factor won't get it. You may need more than one conversion factor. And that's when I call them chained conversions. You just chain your conversion factors together. They're all equal to 1. So it's this number times 1 times 1 times 1 times 1. The key is the dimensional analysis. Does that conversion factor cancel the one you don't want and leave you with the one you do want? And the one you do want is always in the numerator. And the one you don't want is in the denominator, so that it'll cancel. So if we cancel 1 out of here, it leaves you with 1 out of here, but that's not the one you want. But you know a conversion that will take that one to the next step, then you use another conversion factor, cancel that one, and leaves you with another one. I think we're going to do an example like that in a minute. Okay. Oh, I already did that. Okay, so you got it in black and white there. Okay. Oh, in this case, I went from what, centimeters to inches? Yeah, okay, that's fine. Oh, this is a good one. Let's see. There, centimeters. 100 centimeters is what? It's a meter, isn't it? Because a centimeter is 100th of a meter, then 100 of them makes a meter. So this 1 meter is equal to this many inches, 39.37 inches. So when you have a meter stick, lots of times the meter stick is marked in the metric system on one side and the English system on the other side. So you look at the other side and you say, sure enough, it goes out to 39 and about 1/3 inches. Okay. Conversion factors. All you need, the point of this slide is all you need is an equivalence. Something equal to something else. And that can be used as a conversion factor. The only point you have to be careful of is that true? Is 1 inch equal to 2.54 centimeters? Yeah, it is. Or is 1 kilogram is equal to, no, 1 pound is equal to 454 grams on the surface of the earth, right? Because pound is a measure of weight and the gram is a measure of mass. So that's only valid on the surface of the earth. Sometimes you have to restrict the use of your conversion factors. Okay. Oh, there it is. Or this is interesting. If you have 1 pound equals 454 grams. What's the other way around? Right? If this is 1 and that's 454, what if we make this one 1? What is that? As long as they're equal, then we should be good. So what we do is we say 1 pound, I hope I'm not painting myself into another corner, is equal to 454 grams. That is equal to 1. So what if we convert do it the other way? You put the grams on top. There we go. 1 pound there. There we go. Now how would we make this into how many pounds is, if we make this 1, how many pounds would it take to make that? Well, it'd be a fraction, wouldn't it? That's not working. Let's forget that. I did paint myself into a corner. Okay. Oh, this just makes the point. 1 milliliter equals 1 cubic centimeter equals 1 cc, in case you ever need it. So if you want to convert inches into centimeters, we actually don't even need these numbers to answer that question. If you want to go from inches to centimeters, this is where we're starting, and that's where we're going to end up. What kind of conversion factor do you need? Inches on the bottom, centimeters on the top. So your goal here goes in the numerator, and the one you want to eliminate goes in the denominator. Okay. So this is just steps for using dimensional analysis. It's actually, there's probably more, that makes it more complicated than it needs to be. You just want to know starting point, ending point in terms of units of measure. And if you know where you're headed, then you can convert. It's good if you have a conversion factor that you can do it in one step, but maybe you don't. Maybe you need more than one conversion factor. Right, before we do that, let's take an example like let's say I drive from Beckley to Atlanta sometimes because I have family down there. And the distance is about, let's see, I should know this off the top of my head. About 435 miles. Depending on what part of Atlanta you're headed for, because it's a big place. If I want to find out what that is in meters, I don't off the top of my head know a conversion factor for miles to meters. But I do know miles to feet. Right? 5,280 feet is a mile. Right? And then I know inches for feet. Okay, 12 inches, 1 foot. I'm going to have to wrap around here. And then I want to get rid of inches. Now, here's where I convert to the metric system. Because I know that 1 inch equals 2.54 centimeters. Okay? So that gets rid of inches, leaves me with centimeters. Now I can convert to meters. Centimeters, 100 centimeters is 1 meter. So that gives me the number of meters. So say that number is too big. I really want kilometers. Well, if I know that, and I know meters, then all I need is to multiply that times 1 that'll cancel the meters and leave me with kilometers. So that relationship is 1,000 meters in 1 kilometer. So now you've done all your thinking. That's the hard part's done. The rest is number crunching. So how do you crunch these numbers? Well, you just go in your calculator and say that times that. Let's see, most students have algebraic calculators. Just say that times that equals, and then times that equals, and then times that equals, times that equals, times that equals. And then divide by that equals, divide by that equals. And that gives you your answer. Then you don't have to do parentheses. If you do it all in one calculation, you need parentheses. But if you do it step by step like this, then you can use a chain conversion to get you from miles to kilometers. And the only conversion factors I knew were these. Okay. How are we doing on time? When are we supposed to vacate this class? Where is it? I'll give this 11 o'clock. Oh, but we're not going to have lab today, so we can spill over. Let's see. Yeah, that's too simple. The one I just did was more complicated than this. Here's a chain conversion. If you want to convert pounds to grams, but you only know this relationship, kilograms to pounds. And this one, obviously, you know these conversions because K equals 1,000, right? So there's the grams, and the K is right here in thousands. So those conversion factors are easy. It's this one that you need to be given. And you chain those conversions together, and all you got to do is cancel the ones you don't want, leave you the ones you do want. Or maybe you want to leave that, you don't want that. So you cancel it again. It leaves you with the one that you do want. That's all dimensional analysis is. All right, this example is going from New York to Chicago. So if you're going to take a long trip, I don't know, where do you go on long trips? Florida or Myrtle Beach? All right, one thing you need to know is, if you're going to drive it yourself, how much money do I need, either in my hands or in my bank account, to pay for the gas to get down there and back? So how do you figure that? Well, what are the things that you need to know to calculate money that you need in your pocket or in your bank account? You know how far it is, right? Okay, times 2. Maybe plus a buffer for driving around down there. So you need to know distance. You need to know what's the mileage on your car. Right? If you got one of the more recent models that are pretty efficient, you could get 25, 30, 35 miles a gallon. So you need to know that. What's your average? Then what? You need to know how much gas is going to cost you on the way. So that's a big if. That varies. Like when I go to Atlanta, I have just enough gas in my tank to get me across into Virginia. I stop at Withfield and fill up because it's about 30 cents a gallon cheaper there. But then when I get down to Atlanta, price goes back up again. So I have to think in terms of average, right? Or buffer it. You know, what's the maximum amount? Then I'll be sure and have enough. But those 3 facts should get you where you're going. So the distance from New York to Los Angeles, why did it say, okay, there's another boo-boo. This says New York, Chicago, and here we're going to Los Angeles. So let's say we're going to Los Angeles, right? New York, Los Angeles, who would want to do that? I wouldn't want to go either direction. If I were in Los Angeles, I'd want to move to Texas. Or if I were in New York, I'd want to move to, I don't know, Georgia or Florida. I wouldn't want to go between these two unless I absolutely had to. So the distance is 3,200 miles. Right? That's just one way. And let's say your car gets 25 miles to the gallon. And this problem was set up a long time ago. I haven't seen 275 gas in a while. But for the sake of argument, so we start off with miles and we're going to convert it to money, to dollars. So here's our miles, and this in the denominator cancels the miles and leaves you with gallons. So that's how many gallons of gas you need. Then how much is it going to cost? Well, per gallon, it's this much. So that cancels gallons here and leaves you with dollars there. So roughly $350 in whatever this was devised would get you there. You need some to get back. And then if you're going to drive anywhere in Los Angeles, you're probably going to put 30 or 40 miles on your car anyway, each time you travel. So you need to buffer it with a big buffer, like 25%. And then you'll be sure and have enough money. All right. Which of the following is a feature of dimensional analysis? Units do not have to be considered. which of the following is a feature? All right, so that one's false. Units must be considered because they can be multiplied, divided. Yes, that's true. Units can only be divided. That's false. Units cannot be multiplied. Okay, so we found our answer. It's B. You always consider the units. Right, we started off measuring things, and now we're doing calculations. And in the calculation, units have to be carried through the calculation. Right? If you have a calculation that's, let's see, that's meters in the numerator, and something in the denominator, I don't know, meters per second. And it doesn't matter what the number is, we're talking about units of measure. And then you have one over here that you're going to multiply by it. And this one has meters there and seconds here also. Now your answer is going to be meters squared per second squared. None of them cancel, so you have to keep them. So meters times meters is this, and seconds times seconds is that. All right. So probably close to the end, I think. No, we're going to talk about density. Okay. So why do we stick density in here? Well, to illustrate formulas. Chemistry has lots of formulas. Physics has even more formulas. So when you have a formula, think of it in terms of an equation with variables. So density is equal to mass times divided by volume. Okay. Mass can be whatever units you want. Very often when we're talking about density of things, if it's a solid, we're talking about grams per cubic centimeters. If it's a liquid, we usually describe it as grams per milliliter, which is actually the same number for either one. But we have this formula here, and notice that with any formula, if you know all but one of the values, you can solve for the unknown. So if we know mass and the volume that mass occupies, we can calculate its density. If we already know the density and we have this much volume of that object, we can calculate the mass. Anytime you have a formula and only one of the variables is unknown, you can solve for it. What if you do if two of them are unknown? You can't solve it with one equation, right? And does everybody had algebra here? Okay. What do you do if you have two unknowns? You need two equations. Okay? You need two simultaneous equations to solve for those two unknowns. So we're not going to do that. All of our equations are going to have one unknown if they need solving. All right. So let's see. Okay, we made the solids are like that, cubic centimeters. Liquids are like that, grams per milliliter. I left out gases. Why do we go grams per liter for gases? Because you need a lot of gas to give you a measurable amount, right? It's so thin, there's not much mass there. So you need a lot, 1,000 times as much as liquids in order to give you enough to measure. So gas density is reported in grams per liter. Okay. Example, we have a mineral that's been assayed at 7.8 grams and it has a volume of 2.35 cubic centimeters. What's the density? Right? That's simple. You just plug it in the formula. 7.57 grams per cubic centimeter. Now that you know the density of that mineral, if you have the same mineral in another sample and you want to know what's the volume, you just weigh it. Well, actually, technically speaking, you mass it. I never was comfortable with using mass as a verb, so I still say weigh. So if you weigh it, now you know the density, then you can find the volume. How would you find the volume of an irregular object? Right? Regular objects are easy because we have formulas for that. Right? If you have a cube or a rectangle, say, let's make it like this. There you go. There's your substance. What's the volume of that? Well, it's this distance, height, this distance, length, and this distance, depth. Multiply those three together, right? That's easy. Even if you have a cylinder, right, it's just height times area. So you figure the area there, or pi r squared if you know the radius, and then height, and you know the volume. What if your object is irregular? It's like that. How do you know the volume of that? Simplest way is by displacement. Right? You have a graduated cylinder. There we go. Right? And it's marked off in whatever volume units. And you fill it up to whatever. And you have a volume here, initial volume. And then you drop your object into it. As long as the object doesn't dissolve in the fluid or doesn't react with the fluid, then it'll displace up to maybe here. And this is the final volume. So the volume of that object is the difference, right? So if it's like, well, in the lab, we're going to use a cork, a rubber cork, and we're going to drop it in water. And notice the distance, the difference in volume. That's good because the cork's not going to absorb water. But if we use water and we dropped a chunk of sodium in there, then you'd be in for fireworks because sodium and water react violently. So how would you do that one with sodium? Well, use oil. Sodium doesn't react with oil. So mineral oil in here with, that would be a little iffier. You'd be introducing error because glassware is calibrated for aqueous solutions. So if we put oil in there, it might be a little off. But if it's off here by the same amount that it's off here, then it doesn't matter because you're looking at the difference. Correct? Okay. Doctors do physiological experiments sometimes. Not your regular doctor that you go see to diagnose an illness, but research doctors. Those that have MDs and PhDs do research. Sometimes they do metabolic research and they need to know the volume of the patient. So they get this big tank and they put nose clip on you and you jump in the tank and you exhale all the air from your lungs. And usually you'll sink. If you sink, then the volume of the water in the tank will change and they can measure your volume. Okay, what's the mass of 49.6 milliliter sample of liquid which has a density of 0.85? So we know two factors in that formula, and we can solve for the third. There's your unknown, the mass. You can do it that way, or you can solve for the mass first, right? If you have density equals mass divided by volume, then we can say, if we need to know mass, we can say mass equals density times volume. And then plug in the values. Either way works. If you're going to use this formula in some other formula, say you've got a formula that has mass as one of its variables, and then you relate the density to that other formula, then if you solve for mass, then you can put that substituted into the mass in your other formula. So that's one way, one reason that you would want to solve it first and then substitute it. But now we solve for that unknown and find that the mass is 42 grams. Oh, there's one other point I want to make about this. Density equals mass divided by volume. Okay. We can divide information or measurements into two classes. One are intrinsic values. Intensive. That's an intensive value, or an intensity value. That's density. Those are the ones that don't change no matter how much material you have. That's the way density is. There are other values that are like that too. But usually they're ratios of something to something else. Characteristic of a chunk of matter. Whereas these do change. If you have more of the substance, you'll have more mass. Or if you have more of the substance, you'll have more volume. These are what I like to call capacity factors. But your book and other textbooks might call it extensive values. They do change with the amount that you have. All right. One example of an intensive factor that's not a ratio of one to another is temperature. Right? If you have this much boiling water, it's going to be 100 degrees at sea level, 100 degrees Celsius. Or if you have this much boiling water, it's going to be 100 degrees. All right. Temperature scales. We've got three that are used more commonly. Fahrenheit is a temperature scale that we generally associate with weather in this country. And it was the first one that was developed. For the longest time, there were attempts to measure temperature. In fact, even define what temperature is. They knew that things that were hot to the touch had a higher temperature than things that were cold to the touch. And there were various types of thermometers that were invented to quantify a value. I used to have one sitting in my office. It was a gift from a friend. It was let's see, what do they call that? It's the kind that had the colored bulbs in it, and at a certain temperature, the bottom one that rose would have a temperature on a little tag, right? Is that Archimedes thermometer? Can't remember. Or Galileo thermometer, one of those. I don't have it anymore because a cat knocked it off the floor. But that was one attempt for measuring temperature, but it wasn't very reliable, and you couldn't subdivide the values. In other words, it was either what was on the tag or it wasn't. So Fahrenheit was a German scientist who was interested in living systems. He wanted to characterize temperatures that were part of living systems, like body temperature, for instance. So he wanted a system that would measure temperature in a reasonable range that would be associated with body temperature. So roughly 100 degrees would be considered normal body temperature for most mammals. So his 100-degree measure would be right in here somewhere. And then you needed something on the bottom that was reasonable. He picked the 0 down here as the coldest temperature he could get. So he salt, sodium chloride, and ice. So he came up with 0. So then once he had both ends, then all he had to do was subdivide it, 100 units. That's the size of the Fahrenheit degree. And it turns out that water freezes on this system at 32 degrees. It boils, well, way on up here somewhere, 212 degrees. Okay, that was Fahrenheit's system. So we're starting to get a handle on ways to measure temperature. And eventually what was settled upon was a thin tube, well, actually a thin capillary inside a heavy tube for strength. And you don't want whatever's moving inside that tube to be affected by temperature. You only want the temperature that affects that liquid in there from the bulb at the bottom. So that's the bottom of the tube is thin glass. And they use various things, colored alcohol, which is common now in student labs. But mercury worked much better. So they used liquid mercury. And the bottom was a thin bulb that would transfer heat easily. And then the rest of it was thick glass that would not transfer heat easily. And then a capillary, because as you heat a liquid up, it expands, correct? Well, it expands by a certain volume. But if you had a very thick tube in there, that expansion would only give you just a little movement. You want lots of movement. So you can calibrate the length. So you make that capillary tube in there with your mercury, and a small expansion of volume will give you a big length. Okay, so that was the model for the thermometers, that mercury tube. Well, Celsius was a chemist. He didn't care about living systems. He was more interested in ease of calibration. So he said to himself, what language? I don't know, German or Latin. He said, what could be reproduced easily in any lab? Pure water. And then what could you do with pure water? So ice and water is a fixed temperature, 0 degrees. So he said, okay, my scale is going to be 0 here, freezing point of water. And my 100 is going to be here, boiling point of water at 1 atmosphere. They knew enough then that the atmospheric pressure meant just what that. So, and they knew the relationship between altitude, air pressure, and boiling point. So if you're going to calibrate your thermometers, you need to know what the boiling point is at your location. But this was his scale, and then he subdivided it there. So then you had the unit of Celsius degrees was different than the unit for Fahrenheit degrees. In fact, between these 2 points, between 0 and 100, you got 100 Celsius degrees, but between 32 and 212, you got what, 180 degrees Fahrenheit. So 100 degrees Celsius is equivalent to 180 degrees Fahrenheit. So if you're going to convert between the two, and remember, again, nature just does what it does. These temperatures are what they are, and these systems measure the same physical phenomena. So they are related. They're related by the size of the degree, plus, where's the 0? The position of 0 here is at 32 on that scale. So you have to compensate for both of them when you do conversions. Right? So the conversion would be, if you want to measure, if you want Fahrenheit degrees, then you need to take your Celsius reading times, leave myself enough room. What, 180 divided by 100 Celsius plus 32 to adjust the 0 point. Well, that's kind of unwieldy. So your book might say 1.8 instead. But the way I learned it was 9/5. Either way works. So once you know that formula, you can convert either way. Right? If you know Celsius, you get Fahrenheit. If you know Fahrenheit, you just need to solve for the unknown. So you only need to memorize one. All right, so that's two of the systems. The other system was invented by Lord Kelvin. I think his given name was Thomson, but his inheritance said that he had to be Lord Kelvin. And what he was interested in was a system that had no negative values in it. Right? You can get colder than 0 degrees here. You can get colder than 0 here. You end up with negative values. When you're doing calculations with heat and gases, then negative values are not compatible with those calculations. So you need all positive values. So I had to find out, well, where's my 0 point? My 0 point is as cold can get, absolute 0. So Kelvin's 0 point is way down here, absolute 0. That means you can only go up, positive. Okay, so how did he do it? Well, I've got a paper of his back in my office. It's kind of hard to fathom. It's kind of hard to understand, but I found a better explanation for what he was doing, because he explained his new temperature system in terms of thermodynamics. He looked at the work that was being done at the time with steam engines. So he looked at the works of those that were active in the field, like Sadie Carnot, who defined the way steam engines work. But eventually settled, and this explanation, it works better for me. If we have, if we graph degrees C on this scale, increasing that way, and on this scale we have volume of a gas, then Charles' law, which we'll look at later, says that there's a linear relationship, and it's positive. As the temperature goes up, volume goes up for a gas, as long as you maintain the same pressure and the same number of molecules. So you can plot them like this. Right? But that's as far as you can go. Well, that's as far as they went. So Kelvin reasoned, what if we were inside that? You've got the graphing techniques, right? Interpolation versus extrapolation. Interpolation is inside here. Extrapolation is outside the measured range. So Kelvin said, I'm going to extrapolate all the way down to 0 volume and see what happens. Right? So I said that's 0 volume. What temperature is that in the Celsius scale? He said, well, he used several different gases and ended up at minus 273.15 degrees Celsius. That's my 0 point, he said. So my scale is going to start here. Actually, it starts right there. That's 0 K. Notice we don't say 0 degrees K. It's just 0 K. Everything above that is positive. So what would this value in Celsius be in the K scale? 273. And we can leave off the decimals. For most calculations, and our purposes, 273 is good enough. So in the K scale, this position, 0 degrees Celsius, the freezing point of water is 273 K. And all of the values are positive. So that means if you want to convert Celsius to K, you just say K is equal to Celsius plus 273. Or if you know K, you say you get K in a calculation that you do it. And you need, then the question to answer is, what's the temperature in Celsius? Then once you find out what this is, you subtract 273 from it, and that gives you Celsius. Okay, so those are the 3 systems, and we've probably got slides in here that'll explain that. But stream of consciousness told me to go ahead and do it this way. Okay. Oh, we got dates, right? So Fahrenheit came first, 1724. He proposed his system, and then Celsius came later, about 20 years later, and then Kelvin was about a century later. And that's a comparison of the systems. Notice that absolute zero is where, let's see, Celsius absolute zero is minus 273. Kelvin is zero. That's where his system starts. Now, he can never calibrate a measurement at absolute zero. You can't get there. Why? How do you make something cold? Right? Heat always flows from hot to cold, right? So how are you going to get something that's colder than absolute zero to transfer the heat to that so you can have absolute zero over here? It can't happen. You can get close, but you can never reach absolute zero. Okay, so these are conversions. This is the formula. No, that's not it. This is the formula I showed you earlier for Celsius and Fahrenheit. And this is Kelvin to Celsius, or Celsius to Kelvin. If you know those two, then you can solve all the rest. You just rearrange the formulas. This is, I just put this in here because this is if it still exists, I hope that's not a dead link now, but that has an explanation for how this formula was derived. Right? I gave you sort of an overview of what these for. This adjusts the 0 point, and this adjusts for the size of the degrees, but this actually does it mathematically and shows you how to derive that formula if you're interested. Here's another interesting problem. If the size of the degrees are different for these two scales, then they must cross somewhere. At some point, their temperatures must be equal in magnitude. So how would you do that? Use a little algebra. That's exactly what we're going to do. Okay. So if we have this formula, right, we rearrange the formula a little bit. If you've got the same temperature at Celsius and Fahrenheit, then that value should be equal here and here. So we can substitute X for those. This is X and that's X, right? If they're going to be equal. And once you do that, right, so you got X here and X here, just solve for X and you end up with minus 40. Minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. Believe me, it is cold. I used to work for a hotel restaurant supply house. So we had dry goods, canned stuff that just sit on the shelf stable. And then we had a cooler section where we had things like, that's where we processed the meats, made hamburger and hamburger patties and steaks and stuff. And then we had a frozen section where we kept a large freezer, where we kept stuff that frozen before we delivered it to our customers. And that had to be delivered in refrigerated containers. But when some products we made for ourselves, we wanted to preserve their quality. So we'd flash freeze them, very low temperature. We had a blast furnace at 40 degrees, minus 40 Fahrenheit. Well, once a month, like any business, once a month we have to do inventory, right? Keep track of our stock. So we come in early and they have a nice big breakfast, high calorie breakfast, sausage, bacon, eggs, hash browns. And we chow down on free food. And then we grab our clipboards and suit up. And I was a low man on the totem pole. I was going to school then, so I wasn't a permanent employee. So I was given the honor of inventorying the blast freezer. So I'd suit up, I'd be at this quilted coat all the way to the ground. And then I'd have a nice big quilted hat with muffs and big gauntlet gloves. So I'd have to use a huge pen that I could hold in my glove hands. And I'd inventory stuff in that for about 10 or 15 minutes, and then it'd come out and warm up before I could go back in. And the cooler section, you'd go through the cooler section into the blast freezer. The cooler section was like a summer's day compared. So it was great. I'd come out in the cooler section for 10 minutes and go back in for another 15. So that's how I worked my way through college, inventorying blast freezers. No, I did more than that, but that was a challenge. Okay. Let's see, we're going to use temperature scales. How do you deal with a thermometer? Well, we're going to be using Celsius calibrated thermometers. We're not going to be using Fahrenheit. And if you need to do Kelvin in calculations, you'll measure Celsius first and then convert it to Kelvin. But it depends on the thermometer. Some thermometers are calibrated with just single degrees. Right? That's the best you can do. You can read the degree and then estimate between the degrees. Right? So you can do tenths. Some thermometers that you probably won't be using are like that long. So they have a thinner capillary inside, which means it moves farther. And you can subdivide them into tenths or even hundreds. I've seen some thermometers. Now, those are mercury thermometers. Nowadays, we have electronic thermometers, right? And they'll measure down to hundredths of a degree because they use a thermocouple. And you immerse that thermocouple in the liquid or the gas or whatever the case may be. And it interprets the effect of temperature on that thermocouple as a temperature and reads it out. But we don't have enough of those to go around, so you're going to have to do it the old way. And not even with mercury. We have to use colored alcohol thermometers. And they're even worse than mercury. They're at least less accurate. So we're not so dependent upon accurate results as the experience in the student lab. Okay. There's your relationship between Celsius and Kelvin. I think we're pretty close to the end. So, this one would take some doing. If an individual took 300 milligrams of trazodone each evening before bedtime for 1 year, how many pounds of trazodone would he or she consume? Okay. I know what trazodone does. My son had some psychological problems. We sent him to Chicago one time. Puberty hit him hard. He became violent. So he went to Chicago for a residential treatment center. And one of the things that they wanted to do was give him trazodone, settle him down. At a certain level, it becomes sort of sedative. So, but he's okay now. He's 28 years old and just stuck in his room. He's an avid gamer. All the time. He's either gaming or on his computer or something. So he doesn't do too well with crowds. He's agoraphobic, but he's high functioning. You know, his type of problem is on the what they call the autism spectrum. He's not Rain Man, not that type, but he does suffer from this agoraphobia. So all the people he knows are online. Anyway, let's get back to the problem. 300 milligrams, 300 milligrams, right? Each evening, so that's per day. Okay, and we want to convert that to pounds in a year. So we want pounds per year over here. Okay. So what's unique about this problem we haven't looked at before? We have 2 units of measure that are going to be converted. So when that happens, convert them one at a time. So let's convert milligrams to pounds first. Right. So we know that we're given 454 grams is a pound, but grams won't cancel. So we need to end up with grams first. So milligrams to grams, right? Cancel with milligrams. So we got 1,000 milligrams in a gram. So there we're good. Now we're going to convert, let's see. Now we're going to convert grams to kilograms, right? No, grams to pounds, excuse me. Grams to pounds. So we need grams here and pounds here. So 454 grams is 1 pound. Now we got pounds. So we finished with that. Now we're going to chain in here, convert days to a year, correct? So we need the days in the denominator. So the one we cancel needs to be in the numerator, correct? So the relationship here is 365. That's 0.25. But we're not quibbling over fractions of a day per year. So that'll give us, days cancel, that gives us pounds per year. Now that's the hard part. The thinking's done. All we need to do now is crunch numbers. Right? So if you do all that, 300 times 1 times 1 times 365 divided by 1,000 divided by 454. Oops. There it is. 0.241 pounds of trazodone in a year. That's 1/4 pound of trazodone. I mean, when you look at it that way, that's a lot. You wouldn't want to take that all in one dose. Probably kill you. Okay. If you're given a pound of feathers and a pound of lead, the density of each would be the same or different because, well, what would they be? The density of each would be different, wouldn't it? I mean, intuitively, lead is more dense than feathers. Because why? Because the mass of lead is greater than the mass of feathers. Well, yeah. If you're given a pound of feathers, oh, no, the mass is the same. Mass is the same. The volume is different. So to solve this one, you need to look at the formula. Right? And compare the density of feathers versus the density of lead. And in this case, the mass is the same for both of them. So the difference must be the volume. Right? If the density of lead is greater than feathers, then the volume must be smaller because it's in the denominator. Dividing by a very small number makes a larger quotient. So the answer is they're different because they have different volumes. Okay, that must be the last one because everybody's packing up. Yep.